New pictures obtained by the James Webb Space Telescope have staggered experts. Instead of expanding our perspective on the universe, these photos revealed a disturbing reality. Our ceaseless comprehension is lacking in making heads or tails of the possible results of the universe in its starting stages. Where the hypothesis of the enormous detonation, or Big Bang, seems to show up at its limits, this drives us to consider new speculations about its origins. The question arises, how was the universe formed? And why does this new exposure challenge even the most experienced investigators to figure out more about the Big Bang and the complex nuances of the discovery? What about we examine the possibility of the Big Bang itself? In spite of standard thinking, the Big Bang was not an impact in pre-existing space. Maybe it was space itself that started around 13.8 billion years ago, alongside matter and time. An idiosyncrasy in material science and cosmology describes centers where gravity is so intense that the curvature of spacetime becomes boundless. Today, following billions of years since the beginning of the universe, we see that our enormous home is part of a grand cycle. For experts, this represents a vital piece of the universe since its very existence. It's clearly an endless development. However, it's urgent to understand that the universe isn't drifting into past space. Perhaps space itself is constantly stretching out in size, as indicated by current speculations. The first stars began to shine somewhere between 200 to 300 million years after the Big Bang, marking the completion of the so-called Dark Ages. This was when the first radiant heavenly objects coalesced to form mature systems. However, how quickly these infinite systems formed remains a perplexing mystery. A wealth of data emerged through the first pictures captured by the James Webb Space Telescope in July 2022. Experts uncovered that the telescope had identified unique astronomical systems, some of which had already existed around 300 million years after the universe's development. However, rather than the large, permanent structures formed much later, these early universes were considerably more modest and less massive. This aligns perfectly with the scientific model accepted by experts. The density of matter in the early universe was simply not sufficient to create universes the size of those observed today. What started as the identification of 6 shining redshifted spots from the James Webb Telescope ended up triggering one of the most significant cosmic mysteries of recent years. Although these newly discovered universes are similar in age to more recently recorded ones, they are roughly as extensive as our own Milky Way. This has created an intriguing mystery. After examining a series of pictures captured by the near-infrared camera, experts identified the previously mentioned light sources using redshift to confirm that the light from these objects took over 1 billion years to reach our eyes on Earth. Consequently, we are dealing with structures that had previously existed around 570 million years after the Big Bang. By analyzing the characteristics of these systems, it was concluded that the Webb telescope had captured 6 early universes in the photos. Shockingly, these universes were so large that they challenged typical speculations in cosmology. Rather than finding the normal smaller universe structures, the telescope identified universes that were nearly as broad as our own Milky Way, despite having formed early in the universe's history. If we continue to analyze the data gathered by the James Webb Telescope, this gravitationally bound bundle of stars was already more than 10 billion times the mass of the Sun at that time, with one perhaps exceeding 10 billion solar masses. However, whether this scenario is accepted, the mystery remains unresolved. For instance, there would have been considerably more radiant mass in the early universe than previously expected, which presents a problem. The identified objects defy almost all regular cosmological theories. If just one of these infinite systems turns out to be real, it would challenge our prior assumptions. Furthermore, the density of matter in the early universe would have to be several times denser than previously predicted to account for this phenomenon. Another similarly strange explanation depends on how these grandiose systems formed in such a way that remains completely unknown to us. These discoveries and the debates surrounding the Big Bang have prompted several researchers to deviate from this theory. Various astrophysicists with alternative viewpoints feel their perspectives are not being heard in scientific journals. Even those who express doubts about existing theories are often labeled as absurd. But clearly, even experts who still advocate for the Big Bang theory are continually confronted with questions that lack convincing answers. These questions include specific issues like, why and how 13.8 billion years ago, Did something arise from nothing? Could something truly start from nothing? Or was there some triggering event? Or was it all a coincidence? Steven Weinberg pointed out that the concept of time, as we understand it, began solely with the Big Bang. Consequently, this process could not have been set off by something outside of it. A similar puzzling question pertains to the consistency of radiation and density throughout the universe. Regardless of which direction or at what distance we look, on a larger scale we find similar densities and distributions of galaxies, nebulae, and radiation everywhere. Normal inspectors explain this anomaly through the theory of big expansion. However, several experts take this assumption further with a theory of wild expansion. According to this idea, expansion has only paused in specific regions like bubbles and continues indefinitely elsewhere. This suggests that multiple universes could be forming in these bubbles, each with its own unique physical laws. In this model, a key question arises: what if our universe doesn't represent the whole picture? More intriguingly, what if another universe existed before our own? In this case, the Big Bang would become part of a larger cycle. According to this view, our universe is part of a bigger multiverse. Within this framework, the possibility of an eternal cycle of decay and renewal of universes is advanced. However, this is not the only perspective presented in the field of cosmology. In 1955, for example, an article appeared in NASA Space Times arguing that there might have never been a Big Bang because the universe has existed for an infinite amount of time. In this view, the expansion of the universe would be non-existent, and the predictable arrangement of matter could give the impression of consistent development. Also, another interesting theory arises from the domain of quantum physics and string theory. Some experiments have suggested that our universe and everything in it could simply be a flat, three-dimensional image projected onto a surface. Consequently, there is a conceivable idea that our world is the result of a higher-level simulation. While this may sound like the plot of a whimsical science fiction film, it could very well be related to the Kardashev scale, which measures the level of advancement of a civilization based on its ability to harness energy. If there were a Type 3 civilization capable of fully harnessing the energy of an entire universe, it could have created an amazing simulation. Getting it right in such a situation is a truly tangled matter. Exploring the depths of cosmology and the origins of our universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new pictures obtained by the James Webb Space Telescope have reignited discussions about the true nature of our reality, testing established hypotheses, and prompting scientists to reconsider fundamental aspects of cosmological understanding. At the heart of this inquiry lies the theory of how things came to be, a cornerstone of modern cosmology. According to this theory, around 13.8 billion years ago, the universe emerged from an extraordinarily dense and hot state, rapidly expanding, resulting in space-time and matter as we understand it today. This monumental event was not merely an explosion within pre-existing space, but may have included the very origin of space itself. The concept of a singularity, where gravitational forces are so intense that space-time becomes infinite, supports our understanding of this early stage of the universe. However, the discovery of early systems by the James Webb Telescope challenges our assumptions about how quickly systems formed in the universe's earliest stages. These systems detected within a few hundred million years of the Big Bang appear extraordinarily developed and massive, in defiance of assumptions based on current cosmological models. One of the big questions raised by these discoveries is the nature of inflation. As proposed by the prevailing theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand rapidly and decisively. This rapid growth would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, the new findings suggest complexities in the early evolution of the universe that may require revisions to inflationary models. The formation of galaxies like those seen by the Webb telescope pushes cosmologists to reconsider the conditions and processes governing the universe's early development. These massive systems, now crucial in size and mass, suggest a matter density that exceeds previous estimates. The mystery continues as scientists consider how such large structures could have formed and evolved in such a relatively short cosmic time span. In addition, the discovery of these early systems raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up the majority of the universe's mass and energy content. While dark matter is understood to provide the gravitational foundation for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang viewpoint. Some theories propose that our universe is simply one among many in a vast multiverse, each with its own distinct physical laws and constants. These ideas, emerging from developments in string theory and quantum cosmology, suggest a more complicated and interconnected universe than previously imagined. One idea gaining traction is the concept of eternal expansion, in which universes continuously emerge from a larger expanding space. This theory proposes that our universe may be just one bubble among countless others, each with its own unique properties. The challenge lies in finding observational evidence to support such speculative ideas, as they stretch the limits of empirical verification. Another provocative hypothesis is that our universe exists within a simulated reality, much like a computer-generated game. This idea draws parallels to developments in artificial intelligence and computational science, where simulations can replicate complex systems with remarkable accuracy. If true, our perception of reality as a single physical universe could be fundamentally altered, raising profound philosophical and scientific questions about the nature of existence. Moreover, advancements in observational cosmology continue to unveil the universe's vastness and complexity. Telescopes like the James Webb Space Telescope, with its extraordinary sensitivity and resolution, promise to reveal even more hidden secrets of the universe. Future observations may shed light on the earliest moments of the universe, providing insights into its ultimate fate and the fundamental laws governing its evolution. Beyond observational cosmology, particle physicists are investigating the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three major forces, electromagnetism, strong nuclear force, and weak nuclear force, remains a central goal of theoretical physics. Concepts like quantum gravity and string theory offer potential frameworks for understanding these critical interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the nature of time itself remains a topic of intense debate. Time, as a linear progression from past to future, is challenged by quantum theories that suggest time may be nonlinear or even elusive at a fundamental level. Understanding the nature of time within the context of cosmological models could reshape our view of the universe's origins and evolution. Additionally, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable environments elsewhere in the universe. Future missions, such as the James Webb Space Telescope study of exoplanet atmospheres, may provide evidence of biosignatures indicative of life beyond Earth. Notwithstanding these scientific endeavors, social and philosophical reflections on the universe enhance our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration provoke thought and discussion across disciplines. As we stand on the threshold of a new era in space science and cosmology, invigorated by technological advances and theoretical breakthroughs, we are reminded of the vast interconnectedness of everything, from the smallest subatomic particles to the enormous cosmic structures spanning billions of light years. The universe unveils its secrets to those willing to explore. Ultimately, the study of the universe and the origins of existence is a journey that transcends disciplinary boundaries and challenges our most fundamental assumptions about reality. The discoveries made by instruments like the James Webb Space Telescope offer tantalizing glimpses into the early universe, raising new questions about creation, evolution, and the future. As we continue to unravel the mysteries of dark matter, dark energy, and cosmic evolution, we move closer to a deeper understanding of the universe and our place within it. Through collaboration among cosmologists, physicists, philosophers, and technologists, we embark on a grand journey to unravel the cosmos, a mission that promises to reshape our understanding of existence itself. Whether exploring the depths of black holes, wrestling with the motions of distant galaxies, or examining the nature of reality, each discovery brings us closer to unraveling the intricate tapestry of the universe. As we venture deeper into space, driven by curiosity and a desire to comprehend the universe's vastness and complexity, we are reminded of Carl Sagan's words. Asterisk somewhere, something incredible is waiting to be known. Asterisk this sentiment captures the essence of scientific inquiry, a never-ending journey of discovery, wonder, and enlightenment that continues to inspire generations of scientists and thinkers alike. In the words of Albert Einstein, asterisk, the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. Asterisk, as we confront the mysteries of the universe, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of the universe and ourselves. Thus, the exploration of the universe is not only a scientific endeavor but a profound human mission for knowledge and meaning, an odyssey that transcends the boundaries of space and time, inviting us to reflect on our place in the grand tapestry of existence.